我这个问题，资料
I was just thinking.
不比点偏的，他们来打。大家都我他什么？哎，你看可以跟你讲。也就是他们讲讲，感受。
Okay. Welcome back, everybody. So quick reminder that homework 1 is due tonight, 11:59 p.m. on Canvas. And I think I've put a place you can upload it from Canvas. Let's see, any questions about the homework? Or any issues with Canvas? Yeah.
Yes, just the last part of the last question about the geometry of the random points. We can see the histogram of the range and the amplitude of the points, but about what's the geometry of the points? I don't know how to describe it. Yes.
Okay, let me just make sure what we're talking about here. I'm bring it so this is okay. So yeah, so the question is number 4, the last part, you have to sample uniformly on a d-dimensional sphere, that's a unit sphere in d+1 Euclidean dimensions, right? And the last part B is taking pairs of points, computing their angle, right? And then the same thing like we saw in the first intro lecture with distributions, as you increase dimensionality, they get weird. And so when we say geometry is just really any property, like angles are a type of geometry, lengths are geometry, distances are geometries. So it's just kind of anything you can say about the properties of, in this case, angles. So really, if I just replace geometry with the phrase properties of angles. So what can you say about properties of angles? So it's you don't overthink it, what we mean by geometry. It's really think angles are geometry.
Okay.
Yeah.
Yes, thank you.
Yeah, so you should see, just as a hint, as D gets larger, again, something strange going on with angles between pairs of random points. And these are just because they are unit vectors, right? You're just really saying if I give you 2 random directions and it's uniformly random directions because it could be anywhere on the unit sphere. So this is any vector direction is equally likely, if you will. And I just take 2 pairs of those two random directions. They should start behaving again in a way that you may not expect if you hadn't thought of this high-dimensional stuff before. Yeah.
So we just make a speculation based on what we see.
Yeah, based on what you see, describe what you're seeing, and yes, you can speculate. Yeah, what's going on in the limit, if you will. But yeah, it's really, again, not meant to be a tricky question or anything. It's just like, what are you observing? Just describe it. Yeah.
Such a general question. Like, is there a way we can verify the images that we get, like general.
We don't have a, let's say, here's what you should get kind of, Oracle. So, in that sense, no, you kind of have to just be careful and check your code doesn't have bugs, that kind of thing. But think it through, like logically, and the pattern, you should see a pattern. Like if it just all looks the same as you increase D, then you're not doing it right. That's the first hint I'll give. But so you should see some pattern that as you go to D, like something interesting is happening. Kind of like, and if you go back to the first set of slides, or the only set of slides in the class so far, and look at the pattern that emerged from increasing D, increasing dimension there, a similar type of thing should show up here. So that's kind of, you should know it when you see it. And if you see a pattern, you say, okay, that does seem like what might happen. Yeah. There is both of these, A and B, have a mathematical explanation. So you can actually, if you wrote down just a list of numbers, right, x1, 2, 3, 4, and these are just the dimensions after xd, and wrote down what would be their angles, and think about statistically as a probability kind of thing what's happening, you can't actually explain the phenomenon you see. So there is, but that's a much harder problem than just doing it and observing it. So we're not asking you to do the hard problem, which is to explain that phenomenon, but if you do want to verify it like rigorously, you could, and you don't have to do this, which is just, you can actually explain what's going on there mathematically also. Anyway, but like I said, that's harder than actually just doing the code and just observing it and explaining what you're seeing, describing what you're seeing, which is what we're asking. Any other questions about the homework? All right. And just to reiterate, since this is our first homework, we are looking for just everything in a single Python notebook, IPYNB, Jupyter notebook, right? And it should be like, it's a mixture of, there's some math, some description, like text you're writing, and there is, of course, Python code that should all run without error. So import all the libraries you need to run whatever you're running, and it should just run for us without any external, you shouldn't insert any external pictures or, things that don't just run in a nice self-contained Python notebook. So everything, or Jupyter notebook, I should call it, everything should just be there in that one file is the point. Okay. Great. And I'm available after class if anybody needs help or wants to talk about something. I can hang around for a while. Okay. Just to really quickly explain where we are in the schedule. Right now, there's nothing ahead of us in the schedule. It's blank, but I'll just explain what is coming up. So we've talked about manifolds and tangent spaces. I'm going to review tangent vectors, so just very briefly at the beginning here. And then we're going to spend today on Riemannian geometry, which is now adding distances to manifolds. We'll talk about that. That will possibly get done today, but might bleed over into a little bit of Thursday's lecture. Then after today, or after we're done with Riemannian geometry, we are done with the mathematics introduction part of the course, and we will move on to actual application of all these concepts, these geometry concepts, to data analysis, machine learning. And so on Thursday, we're going to, if we stay on schedule, be introducing our first application of some of these geometry methods in data analysis, and we're going to look at manifolds of known data types, so data types that live on manifolds. And so one, like I mentioned this at the beginning of the course, one very simple example is spheres, so positions on the Earth, directions. Again, if you don't care about lengths of vectors, you just care about their directions. You can have things like wind direction, data like this, direction that an object is moving in kind of like, trajectories and things like this. So there's that type of data. But we're going to talk about another example, which is shape data. And I mentioned this again in the intro lecture. And this is where our manifold is all possible shapes objects could take. And that could be 2D like objects or three-dimensional objects. And we want to analyze their shape. That'll be we'll learn that'll be a manifold representation of shape. And we'll look at how to do simple analyses like compute averages and variability of these manifolds. So that'll be what's coming up the next few days, 3 or so lectures after today's lecture. And there will be a homework 2 released probably very soon, probably this week, I would say. That's going to talk about some of those things. Okay, so that's what we're look forward to. Okay. Right, so let's review where we were last time. I'll just mention tangent vectors and spaces. When we have a manifold M, and we're at a point P, we were saying that a tangent vector at P, using the letters like V for vector, was really, the way to think of it is as a velocity of a differential curve that's passing through P. And this curve, let's call it gamma. And again, remember, there may be multiple curves that pass through P with the same velocity, and those would be in an equivalence class together. And that equivalence class of curves is what we define to be the tangent vector V. And if we think of all possible tangent vectors at a point P, this forms a vector space, which we call the tangent space at P to the manifold M. Okay? And without reviewing all the math details, there was a couple of different ways to think about this. One is just as velocities. The other was, we said that these V's can be thought of as a derivative operator, more specifically a directional derivative operator. So if I have F is a real valued function on my manifold, and of course it has to be differentiable, then I can write down VF to mean what is, so F is just a function over the whole, it just assigns a real value to every point of the manifold. But if I were at the point P, and I wanted to know how is F changing in this specific one-dimensional direction, then this directional derivative is what tells me that. And again, V is really only really defined at the point P. You can expand this if you have V, which is a vector field defined of the whole manifold, and then I'd want to evaluate this at a particular point P to get a number. But let's just say V is only the single tangent vector at a tangent vector at a single point, then this VF is really being evaluated at the point P. And what we mean is that you take the derivative of F composed with gamma. I should take gamma of epsilon at epsilon equals 0, where gamma again is a curve that has derivative V, velocity V at the point P. So we can think of, because gamma takes me from the real line or an interval of the real line, or I should specify that gamma of 0 is equal to P, and D gamma the epsilon at 0 is equal to V. I need a curve that satisfies this property. And then this is how I define the direction derivative. And of course, gamma goes from an interval, which is part of the real line, to M, and then F goes from M to R. So this composition is really just a real function. And that's why I can take its derivative just like any real valued function. And that lets me define what I mean by a directional derivative. And that's how we can think of tangent vectors as directional derivative operators. Yeah, question.
Sorry, I'm just really confused that you're calling it a tangent vector, but it maps to R. R.
The vector, the function maps to R. The vector you can think of as a thing which takes in any function you want and produces a number, which is this number. So if F is any, I should say, for all F that are at least C1 differentiable functions from M to R. So you give me any function that I can take a derivative of, and VF is defined as this derivative.
VF is the tangent vector.
Yeah, V is the tangent vector. And so this is again, V is think in this sense, we're thinking of this as an operator that operates on functions. So think of this like this notation, this concatenation is like you're used to seeing things like A times X for a matrix A and a vector X, and that's just concatenation. It's an operator on a vector. We're thinking of V as an operator acting on functions.
It's real value, just scalar.
The output of V operating on F is a scalar, yes. So ignore this notation for a minute. Is this, let's just look at this side. Is that equation clear? Let's focus on this. If I compose a curve.
It's clear what it means. It's clear that it should be real valued.
Yeah, okay, good.
Scalar.
Yeah, that's right.
That's what confuses me.
And that's what VF is. So V by itself is this tangent vector, yes. But it's also an operator that if I act on a function, it gives me the directional derivative at that point.
So does the tangent vector have the same dimension as the manifold?
Yes. This is if N's an n-dimensional manifold, this is an n-dimensional vector space, yes.
How do we see that this is n-dimensional then? I just think it seems real value.
So V is not real value. You can write it. So let me write it down. Let me do it the following way. So let me take the second view. It's a great question. Let me take the second view of vectors, and then if it's still not clear, let's pick this back up. I'll check with you, see if it's clear from this second view. So second view of tangent vectors. Well, I guess. Sorry, the two views are, yes, velocity and directional derivative operator. But then remember what I really mean, not the second view, but the way to write this down is to write anything down really on a manifold, I need a coordinate system. So let's say around P, I've got a coordinate system. I'll call that little x. And it's just a small patch open set here around P. I mean, it could be small, big, doesn't matter. Open set around P that maps to an open set of Euclidean space, let's say. And to write down V, again, remember each of these coordinate vectors really define vectors up here, the derivatives of the coordinate lines. A coordinate line here, if this is, say, x1 dimension, this is x2 dimension, then a coordinate line here, it has a velocity, which I can think is the partial derivative operator ddx1. That's this vector here. This vector here is ddx2, and so forth and so on up to ddxn. It's the partial derivative with respect to that coordinate axis. Okay, and these these vectors, I can think of them as the coordinate vectors down here in my Euclidean patch, but I can also think of them simultaneously as the tangent vectors, the velocities of if I drew these coordinate lines back up through x inverse as curves on the manifold. Okay, just like the gamma curve, these coordinate axes map to smooth curves on the manifold. Okay, so they kind of have this dual way of thinking about them. But so what I can do is I can compose x inverse with f, and then I can take the derivative, partial derivatives of that function. So that function is now the f function. If I do f composed with x inverse, this is really a mapping from Rn, or some patch of Rn, to R. So I can take its partial derivatives with respect to the n coordinates x1, x2, out to xn. Okay. Now V can be written because these ddx1, ddx2, etc. form a basis. They're linearly independent. They form a basis of this n-dimensional space. I can write V in that basis. So V in a specific coordinate system looks like VI times ddxi summed over the n basis vectors. Okay. Now, what do I mean by VF now? The directional derivative of F in the V direction. Again, if I pull the function F back to here, as so, then the directional derivative is just take the derivative with respect to each axis times that component of V. So think of this is a derivative operator. If I write, I'm just going to write V first. I'm just going to copy this here. Oops. Okay. And now I'm going to flap F on the right of it, that concatenation. Now this should feel more comfortable to you, concatenating a derivative operator, differential operator with a function. I just mean apply the ddxi to F, right? And I bring that inside the sum. And I just get multiply VI times the corresponding partial derivative of F. Okay, and this is, if you go to multivariate calculus book, right, this is one of the ways to write down the directional derivative of a function in n dimensions. Does that help explain how I went from an n-dimensional thing to a output of a real number? And I should say you evaluate this at, you know, whatever coordinate P is at, right? So I evaluate this, you could call it, let's call it 0. And x1 to xn, let's say at 0 corresponds to value P. But anyway, evaluate at whatever value, whatever position corresponds to point to P on your manifold. Does that help? No? Where's the confusion with the second formulation of this?
If I'm the only one confused, we can.
No, it's fine, but
I just don't see why it's a vector, because again, ultimately, some VI, they're scalars, you're summing scalars.
Yeah, these are scalars. This is a scalar. I'm summing a bunch of scalars, and yeah, this is supposed to be a scalar, the directional derivative at P in the V direction.
The only way I can see that this corresponds to defining a vector, a tangent vector, is if you have multiple F.
So look, so this is, let me write this one more way. I mean, this is really just multivariate calculus we're doing here. I'm going to write this as the usual inner product between n-dimensional vector V and rad of F. So you see how I've got n-dimensional vectors. I mean, these are a vector. I take a dot product, inner product. That's another way to write down the definition of a directional derivative, is that you take the gradient of a function, you dot it with the vector. That's the directional derivative in the v direction of a function f. So I've got n-dimensional vector, dot product, I get a scalar. So that's how I went from vectors again to scalars, and I'm doing derivatives here, directional derivatives. And one last look at this. If I think of f like level sets, where f is, equal along the level set here, just let's do 2D. The gradient is the direction of maximal change. It's always perpendicular to the level set. So this is the grad f direction, these vectors. And then if you want to know what is the change of f instead of in a different direction, let's say v, what you do is you take the dot product between these two vectors. That gives you how is f changing in any arbitrary direction v. That's what this equation is doing. Yeah.
So normally, like a standard Euclidean space, when we first learned vectors, we're taught that the directional derivative is defined based on the vector previously, but in this case, we're defining a vector as an operator that is the directional derivative.
Yeah, so this is, I mean, this is like just multivariate from here on. It's just like if I was in Rn for multivariate calculus. And yeah, and the way you've probably learned this in multivariate calculus is either this dot product formula, or you could write it as a limit v, f of x plus v epsilon or something like that with a limit in epsilon. Or you wrote out this partial derivative. So it's like at least 3 different ways to write it. But what you probably did not learn in multivariate calculus is that, I mean, this is just a linear operator. And so if I abstract away that I'm doing derivatives in calculus and everything, and think of this as an abstract basis for an operator space, then I'm really writing down an operator in a specific basis. Forget about whether there's derivatives involved. This is just linear algebra. Then this V is an operator, like a matrix would be an operator acting on a vector thing. Yeah.
The space of operators, the tangent space.
Exactly. Yeah. And so the space of operators that behave like this forms an n-dimensional vector space, which we call the tangent space. But it's not, for our purposes, intuitive maybe to think of them necessarily as operators, but we will use them as derivative operators, and we will think of them geometrically as velocities of curves. Both, they have this dual kind of life as both things. So let me try to get out of the way of this equation here. Yeah, if there was a question up here, yeah.
Why are we computing v of f?
Sorry, say again.
Why are we computing v of f?
So right now I'm computing it because I just want to explain what a vector is. And what we'll see is later, actually just today, this lecture, we'll actually think of v more in the geometry sense as the velocity of a curve, because now we're going to be interested in finding curves that are as short as possible between 2 points. That's our geodesic computation we're going to do later, just after this review. But why do I want to do this as VF? Why do I ever want to compute this? Again, this gets into actually just to even define what is a gradient when we're talking about manifolds. This depends, this is a Euclidean definition, like what I wrote here. This is actually not yet defined for any manifold because I haven't defined this inner product. So I should say this equation I was using, this is specifically Rn, because I have an inner product in Rn. I don't have this inner product defined with any arbitrary coordinate system. So I want to be very careful. This was an analogy to what you know from multivariate calculus, but in manifolds, this analogy we don't yet have. So why am I doing this? We're going to be able to eventually define what do we mean by grad f through this definition, and gradients like the main tool mathematically in all of machine learning. How we learn anything is almost always through gradients of functions. And so everything we're going to do in manifolds in machine learning and data analysis for manifolds is going to require some kind of gradient descent, gradient calculations. And so that's the primary reason to think of this VF operation. There's probably some other applications we're going to come across that I can't think of off the top of my head, but that's the main one. Yeah, thanks for mentioning that, because I kind of bled into our multivariate calculus analogy with this last equation. This is all good to go for manifolds. This, where if I stop right here, I do have, if I have a coordinate system xi, I can write this partial derivatives. That's totally fine. I can write my v's in that basis. This is all fine. This last thing I did was, again, an analogy to what you do in Rn with the dot product, but just to be clear, we don't yet have a dot product on manifold, but we will at the end of the day today. But right now we don't have this defined yet. Okay. Other questions? Yeah. So if this isn't super crystal clear, don't panic, but think about it in the notes, and really think about I think this piece right here as v is a directional derivative, and don't get too hung up on the notation vf. Just think, okay, I know what a directional derivative is. This vf is just the notation for that thing, which is to say this kind of thing. Okay. Yeah.
Explain a little bit again about like what's the expression v equals the sum of xi partial x. Like what is n there? It's like
so the
coming up to
yeah. So n is the dimension. This is dimension of our manifold, and therefore also the dimension of our vector space. And another way to think of it is I have coordinates x1 through xn that I'm mapping my manifold down to locally at least, and that the tangent vectors to each of these axes, the coordinate line x1, x2, and so forth, are these partial derivative operators, ddx1, ddx2. They are tangent vectors. They're the tangent vectors to the curves up here, if you will, and they form a basis for this vector space. So if I have a basis for a vector space, I can write any vector in that vector space, you know, in that basis as a set of n numbers. And so these vi's are just the coefficients in that basis, v1 to vn. So this is just saying write v in this basis. That's all we're doing, is writing it in the ddxi basis.
we are like taking derivative of each coefficient with respect to x. We're taking
So v, we're not taking any derivatives with respect to of v. We're taking derivatives of the f, or any function you put on the right side of this, because this is the operator. The function will go here, and it means this is sitting here waiting to take a derivative of a function. It's like an operator sitting there waiting to do its job, which is take a partial derivative of some function and give it. Yeah. So yeah, this is, if you haven't thought of it this way before, this is a bit of a paradigm shift in your thinking, that a partial derivative ddxi is not just a calculus thing. It's an operator. It's a vector now. It's an actual vector in this coordinate. Okay, so that's one thing that I think is a little bit uncomfortable for people the first time you see it. And yeah, so if I think of a coordinate as just a grid at a point, I can think of the derivative to that grid, those curves, as these partial derivative operators. They're tangent vectors. They're also derivative operators. Okay, so they have, again, this dual purpose in life. Okay. Yeah, so yeah, good for everyone to ask questions and slow this review down, because it takes some effort to think about and get your mind around it. Okay. Right. So the The other thing I was going to review was going to be, we talked about just briefly at the end of last class. I'm going to skip this review because it's not really relevant for our current discussion. It'll come back later, but I'll just briefly mention it. We talked about derivatives of mappings F from M to N. And we said that they, if I have a manifold M and a manifold N, and these can be different dimensions, and I have a point P, and where it maps to F of P, then the derivative mapping, which we can write as DF, I think in the notes I write it as F subscript star. That's the same thing. It's just different notation people use. But this derivative mapping is analogous to the Jacobian matrix we have of multivariate to multivariate functions. And you can think of it as, again, an operator that takes vectors in the tangent space at P, M, to tangent vectors in the output space, P, F of P, of the manifold N. We're not going to use this for a little bit later. We talk about neural networks. It'll turn out that these Jacobian mappings are useful to understand, but in neural network layers. But I'll just kind of leave it at that to say that I can write this DF if I have an X coordinate system and a Y coordinate system. I can write it again, I can write F as a mapping really down here in coordinate systems, and I can just compute the Jacobian matrix of that mapping in coordinates, and I'll get, if this is, if this is Rm, and this is Rn, then I'll get an N by M Jacobian matrix of this mapping down here, and that's how I do actual calculations of Jacobians or these derivative operators. But the intuition is that this is you can think of this as a matrix down here in this basis, in this coordinate basis. And again, this is the ddxi and the ddy basis of these two coordinate systems, the tangent vector basis. But what is it really doing? Intuitively, it's saying, if I take this operator and multiply it by a vector v up here, it will tell me what's the vector. This vector here will be df applied to v. And it's saying that if you perturb your point P on M, then the change in the output of F is this vector here. So it's kind of like a analysis of small perturbations here lead to what perturbations here. And as we also talked about, which again, this will come back later, is backpropagation is taking a gradient, it's going the opposite direction, have a gradient vector here of a function, then the transpose of the Jacobian pulls it back to the chain rule of the gradient in the previous space before I did the F mapping. So anyway, we won't use the concept of a derivative again, but that's what we ended on last time, just to review. We aren't using it today, but we'll use it later. Okay, so what are we doing today? Today we're doing, like I said, Riemannian geometry. Oops, I was doing a blackboard font here, so sorry. Riemannian geometry. And again, this is like the next section of the notes. I think it's section 3 or maybe it's 4 at this point. I think it's 3. And every time we added a section, we added more structure to, we start with the sets, right? Sets. We added a concept of topology. Okay, that gave us the structure of what does it mean to be continuous. We then added manifold. Manifold told us what does it mean to be locally, what does it mean locally to be a Euclidean space. We then added differentiability. So our charts gave us ways to compute derivatives. We didn't talk about integrals, but you can also do integrals in charts. And so we added calculus there. And now with Riemannian geometry, we're going to add a notion of distances, which we don't have yet. If you just give me a manifold, distances aren't defined. There's nothing, a coordinate chart has no units. And if I change coordinates, it would be a different set of units anyway. And so there's no well-defined notion of how far I've traveled on the manifold at our current time. And so that's what we're going to do with Riemannian geometry. Add a concept, a units of distance, and how do you measure distances on manifolds. Okay. So the first thing I want to do is ask a question, hopefully an easy question. If I'm in Euclidean space, let's say R2, R3, what have you, I give you point A, you're standing at point A, you want to get to point B, what's the quickest way to get there? What path?
Straight line.
Yeah, straight line. So this is, everyone knows this, I missed it, but you know, roughly, straight line, okay? Now the hard question, why did you know that answer? Why did you know that a straight line is the shortest path between 2 points? Yeah.
Hypotenuse of a right triangle.
Wait, sorry, say again?
It's hypotenuse of the right triangle. So
Okay, so hypotenuse of the right triangle.
you know the any side of the triangle. is
Right, if
less
I had
than
like a
sum of
coordinate system, like this is the X direction, the Y direction, then I would know that this is with trigonometry rules, I would know this is sort of, okay, Pythagorean theorem, A squared plus B squared, whatever. Yeah. But when you were, let's say, 2 years old-ish, you just started walking, did you know that? Pythagorean theorem. And did you know about straight lines were the quickest way to get somewhere? So when I say, how did you know that? I don't mean mathematically, how did you know that? Just as a person in the world, how do we know that going from point A to point B is the quickest way to get where we want to go?
You just run there.
You see point B and you just walk towards it, right? I
And
mean,
if you deviate from the side, you'll have to kind of take a little bit more steps.
right. Yeah. So we know intuitively. So what I mean is intuitively, we know a straight line is the fastest way. We know that if we deviate, it's going to take us more steps. We know this, but again, why do we know this? Why is this this is something deep in our intuition? When do we learn this, or do we just, is this inherently, you know, in our genetics? It's something we just know.
It's just I think our brain in the background compute a lot of actually multidimensional calculus, because like spatial dimension and everything, humans are good at it, but we are not consciously calculate all of this. Our brain just does this for us.
Yeah, exactly. So that's, I think, kind of how I think of it also, is in a sense, is that our brains are very good at minimizing energy, minimizing loss, and maximizing reward. And if you see something straight ahead of you, your brain also understands more physics than you realize. that the laws of motion, if you look at Newton's equations, that's the best way to get from point A to point B. You can derive this mathematically from physical principles, but we don't actively think of these derivations when we're little kids and know that we want to get a cookie that's on the table, we go straight for it, right? So anyway, my point is that your brain is actually doing a little bit of geometry and physics almost subconsciously. But okay, so now let's talk about mathematically what's going on when we want to get from point A to point B. We're going to take a long mathematical journey here. Well, I guess it's not that long. It's maybe about 30 minutes is how much time I have. And at the end, we'll see why the shortest distance between 2 points is a straight line. Okay. So let me generalize the question a little bit more. If I give you a curve between 2 points A and B, again, just in Euclidean space, and I'm going to call this curve gamma. Actually, sorry, let me make this P and Q. Because I want to use A and B as my time interval, I think, just to match the notes. Okay, so I've got a curve gamma. From some interval in time A to B to some Euclidean space Rn, and gamma of A is at where I'm starting, gamma of B is where I'm ending, and I want to know, now gamma is not the shortest path necessarily, it's just some curve, and I want to know what's the distance I traveled from P to Q if I had stayed along the path gamma. Like maybe gamma's a curvy country road somewhere. How long of a distance do I have to travel to get on this curve? So how would I compute that? Yeah.
Path integral.
Yeah, integral, path integral, exactly. I'm going to integrate over my time parameter, a b interval. I'm going to integrate the derivative, right? And this derivative is a d-dimensional vector, or sorry, n-dimensional vector. So what am I going to do to this vector? This is the velocity, which has direction in it. What am I going to do to get just the distance in the end?
The t,
Who said this?
the t and the differential.
Yeah, I'm going to take the norm or the length of this vector, right? And integrate that over the curve. Okay, and this is the length of this curve, or really curved segment M. Okay. So you take the speed of your curve and you integrate it over the length of, over the time interval. And think about this speed, right, is in distance per time interval, right? So let's just say it's like meters per second, right? Something like that. And you're going to integrate over time. So that's going to get rid of this divide by seconds in the interval, and you just get in meters. This will just be in meters, the length, the units, right?
I guess here we also see that the straight line will be the shortest because derivative of the straight line, right?
Yeah, so the punchline is if I wanted to find the shortest path between P and Q, I'm going to take a derivative of sorts of the length function here, and I'm going to find a zero of that derivative, and that is a straight line. Now there's a little bit of work to get there, because what do I mean by a derivative of a function which takes curves as inputs? Okay, this is not a trivial thing. This I want to take something that looks like a dd gamma, right? But that doesn't make much sense to take the derivative with respect to a curve. We can do this though, and we'll see how. If you haven't seen variational methods, this is something called the calculus of variations. So you can take derivatives of things which are really functions on things like curves. Okay, so that's what we have to do to get the length of a curve or a curved segment. Now I want to do this on
Hey, we've lost you on the video stream.
Oh, thank you. Yes, please do speak up. There we go. Sorry. Yeah, thanks for speaking up. It definitely catch me if felt like the word of God coming down from there. But I appreciate it. Yeah, so just I'll repeat myself one more time. So yeah, this is how we do lengths of curved segments in Euclidean space. This curve lives in Rn, but now, for the purposes of this class, of course, we don't live on Rn, we live on M, which is an n-dimensional manifold. And now let's say gamma is a curve from a point P in M to a point Q in M. Why can't I just do this? Were we missing? Kind of already hinted at it over there. But I'm missing something. I can't just do this equation. Yeah.
We cannot take the derivative on the manifold.
So let me just say, that's partially correct, but let's just say d gamma dt, let's just say that we do have this notion of velocity. So I can talk about this d gamma dt as the velocity of the curve. So the derivative, meaning in with respect to time, is just the tangent vector of the velocity. So let's say we have that, but then there's one other element here that we don't have. In this equation. There's only a couple other things going on in this equation. So what could we not do here? So say I can do this. This is good. This is the velocity of the curve. Yeah.
There is no notion of distance on the manifold, so we cannot take the norm.
Exactly. This is what we don't have. This guy right here, the norm of a vector. Okay. And so you might ask, let me write this d gamma dt as v, just to give it again a name. D gamma dt is v. Why couldn't I just say write this as I have all the way on the far side in an x coordinate system, and then I could write this v in some coordinate system as an n-dimensional vector, and then just say that the norm of v is equal to the square root of this gets tricky when I'm doing v1 squared out to vn squared. So why would this be problematic? And this is what the norm of a vector is, right? In Euclidean space.
It means in vector space, right here.
Yeah.
Is not like plane.
Well, but the v lives in a plane, in a hyperplane, I should call it, n-dimensional vector space, which is the tangent space. So vector space is okay. V is the vector space. You're right that manifold is going to be non-linear, possibly, and that we wouldn't want to take like the norm of Q because it's not a vector really, but V is a vector, and I can write it in a basis, and I can write this down. But why would that cause me trouble if I did it this way? Yeah.
Is it computationally expensive for higher dimension?
It is expensive, but I think there's no way around that, honestly. So we're stuck with expensive computations if you have high dimensions. But you're right, that dimensionality would make things like this more and more difficult as dimension goes up. Let me ask the following. What if I wrote V in a different basis? Let's say I have a, because remember, coordinate charts, I've really got an infinite number of choices. As we saw with the sphere, I can put the stereographic projection. I could do spherical coordinates like the longitude, latitude lines. Those are two different coordinate systems. I can put the same point in two different coordinate systems. What happens if I write in a different coordinate system? What's the bad thing that could happen if I wrote this in a different coordinate system and wrote the same equation here?
They have different norms.
Sorry, speak louder.
Yeah, they might have different norms.
Yeah, exactly. So if I write this in a completely different coordinate system, I can get a completely different answer. So the norm in a coordinate system is not a unique property of the vector v. This is generally a problem with coordinate systems, that if I do operations in a particular coordinate system, sometimes if I change the coordinate system, I'll get a different answer. And then that property is not going to be inherent to or it's not going to be a unique thing you can do. And with, it's not, I should say, invariant, let's say, to the choice of coordinate systems. And that's typically a bad thing. Okay. So we need to be able to define the length of a vector, which doesn't depend on the coordinate system. Okay. Okay, so And that's where Riemannian geometry really starts, is with that definition. And what we're really going to do is we're going to define an inner product on our tangent space. And you can always get a norm from an inner product. And so we're going to call this inner product a Riemannian metric, which is, I think, a terribly confusing terminology. Metric, we've already used that word for a distance, right? A metric, or metric, like when we had a metric space, the metric was the distance function. Now it means something else. It means an inner product function. But from the inner product function, the Riemannian metric, we'll be able to define a distance. So it's very confusing. But the Riemannian metric is not yet the distance, it's the inner product that will let us define the distance. So yeah, let's write down the definition. What is a Riemannian metric? A Riemannian metric is a inner product assigned to, I'm going to write it in the following way. At every point P, let me say on a manifold M, we're going to have for every every point P in our manifold, the Riemannian metric is going to be this inner product. And writing it as like two dots, meaning two slots here for things. It's going to take 2 points in TPM, that is two tangent vectors at P. And it's going to return a real number. Just like we're used to, the dot product takes two vectors and returns a number. So it's just a dot product on this particular vector space. Okay. And what does it have to satisfy to be a valid inner product? We have to have that it's bilinear. Bilinear means it's linear in the first vector and also linear in the second vector. Again, just like an inner product. And it has to be positive definite. And sorry, I'm not writing out the math formula for bilinear. I think everyone knows what it needs to be linear. We get linear this and linear that. Positive definite, I will write out. It means that you take two vectors v. Sorry, you take one vector and you dot it with itself, the inner product with itself. And this number is greater than or equal to 0. Let me write it the following way. It's greater than 0 if v is not 0. And of course, by linearity, it's equal to 0 if v is 0. This 0 dotted with 0 has to be equal to 0. So, but if v is non-zero, it's strictly a positive thing. And positive definiteness is the thing that really makes inner products act the way we expect them to when it comes to length, because then we define the norm of v. And sorry, I should say this is for tangent vectors at the point P again, because there's an important thing here to say about this dependency on P in a minute. But the norm of v, just like again in Euclidean space, I would say it's the dot product of v with itself, and then take a square root. That's how we usually define the length of a vector in Euclidean space. You can say the dot product with itself, square root. And again, in Euclidean space, that's like v1 squared plus v2 squared, etc., and then square root. Now, this means that this condition, positive definiteness, means that any non-zero vector is going to have positive length. It's going to be this square root. You can take this square root, first of all, like if this was a negative number, I'd be in trouble. If it was 0, it'd be weird to have a non-zero vector with 0 length. So this positive definiteness makes lengths work the way we expect them to. Any questions so far? There's one more property, but this is what it means to be a inner product in any vector space, honestly, these two properties. The third thing we need for manifolds is these manifolds are differentiable manifolds. I should say this, I should have said this is a C1 manifold. It's a differentiable manifold. We also need that this inner product, which is defined at each point, you have a different tangent space, you have a potentially different inner product. But because of differentiability, we would like it to be the case that if I move around the manifold, that this inner product changes smoothly in a differentiable way. Okay. And so what do we mean by that? To be a differentiable inner product is the same way we talk about anything on the manifold being differentiable is we drop down to a coordinate system and say it has to be differentiable if we wrote it in a coordinate system. Okay, so let's draw a picture here. I have my manifold M. I'm at a point P. It has a tangent space TPM. And I can talk about two vectors. Let's call them U and V. Okay, and I can take their inner product that I've just defined, except for the last smoothness property. I can take their inner product here. Okay, now what I want to do is write this down in a coordinate system. I have a coordinate system X, which again, there's an open set here that I'm mapping to a coordinate system. And just like we just did with tangent vectors, in this coordinate system, again, if I think of this as x1, x2 out to xn, I can write u and v in that coordinate system. And I'm just going to write them as a kind of column vector. And again, this would be like u1 times ddx1, u2 times ddx2. It's in that ddxi basis. The dxi basis for the tangent space. Okay, that's what I'm writing this. Now, if I want to say u dotted with v, again in Euclidean space, I just say u1 times v1 plus u2 times v2, et cetera, et cetera. But now I can be much more flexible than that because I just need to satisfy these two rules, bilinearity and positive definiteness. To do that, again, written in this coordinate system, I just need to be the case that I write u vector over here. I write a matrix. Little g here is going to be a matrix. Okay, I'm going to transpose this vector, and then on the other side of the matrix, I'm going to write v vector again in this basis. The G matrix, again, I'm in this basis for this specific coordinate system, is an n by n matrix. And this is the Riemannian metric written down in this basis system. Okay. And so I can write any dot product in coordinates this way. To be careful here, in order to, oh, I left off a property actually. Sorry. Come back over here. Property 1.5 should be property 2, property 3 probably. Anyway, is that this needs to be symmetric. an inner product should be symmetric, meaning UV is equal to VU if you flip the inputs, right? That's also a property of inner products, which I left off. Sorry about that. So yeah, symmetric. I realized that as I started to think of this matrix. So for this matrix to satisfy those three properties, the first property, bilinearity, this is a bilinear operation no matter what G is. So that's check. You can see that. Symmetric. For this to be a symmetric operation, meaning I can flip U and V, what do you think I need G to satisfy? I think,
To be symmetric.
yeah, to be symmetric. So if I just take the transpose of this whole equation, then U would go over here and lose the transpose. V would go over here and get transposed, right? And G would be transposed in the middle. So for this to all be the same, if I flip U and V, I should be able to transpose everything on here. That means I need to be able to transpose G and not change. Yeah, question.
What is G actually here?
It's this matrix.
Yeah, but what is each value?
It's anything. So Riemannian metric is a thing you impose on a manifold, just like the differentiable charts are things you put on that you have to define to put on the manifold. So yeah, that's a great question. G is going to be a set of n squared. We'll see with symmetry, it's really n choose two different values that I'm going to put on my manifold to define what is an inner product on my manifold. There is no unique metric. I can define multiple metrics. I can change the metric on a manifold. It changes the notion of distance, is what you're kind of defining what you mean by distance on the manifold. Yeah. Okay. Okay. So yeah. So to satisfy the symmetry property, I'm going to need this property 1.5 I have over there. I need G to be equal to its own transpose. I need G to be a symmetric matrix. Another way of saying that is that these entries Gij have to be the same as the Gji entries, right? If I flip this matrix about its diagonal, I should get the same matrix. Okay. Property number 2 is a little bit trickier, and if you haven't seen positive definite matrices before, you may not have seen property 2 yet. But does anybody know how to make an equation like this satisfy positive definiteness?
For any U and V.
So think of it in terms of the matrix properties. I have matrix G, and if I gave you a V over here and a V over here, I want V twice. I want this to be a positive value always. Anybody know how to ensure that in a matrix? And it's a symmetric matrix specifically, a symmetric real value matrix. So to be clear, these are all real numbers. But yeah,
The eigenvalues are greater than 0?
yes, absolutely. So positive definiteness of this inner product means this matrix has to be what's called a positive definite matrix, and it means the eigenvalues of G are strictly greater than 0. Okay. And if we're not going to, I'm not going to prove that statement, but if you want to kind of convince yourself of it, remember that if I have a symmetric matrix, I can write down the eigenvalue decomposition, eigenvector eigenvalue decomposition. So I have all real eigenvalues for any symmetric matrix. And if you wrote down your vectors in which was the eigenvector, which were eigenvectors in G, and then thought of multiplying 2 eigenvectors together, I'll get the eigenvalue right out. And so if any of those were negative numbers, I would start to break this thing I want to be true. So if you think about, you can write this guy down as a, if it's a symmetric matrix, V, lambda, V transpose, where V are the eigenvectors, lambda are the eigenvalues, and think about, I'm going to need all these eigenvalues to be positive, or else I can get vectors that go through and give me either zeros or negative number which we get. Okay, so so this is what I need for my little g matrix. And again, it's weird that we're using a little, I realize, a lowercase letter for a matrix, but that's again the notation and Riemannian geometry typically that this little g matrix is the Riemannian metric. It satisfies all these properties. And then the last thing that I was going to say, the property we need for on a smooth manifold, a differentiable manifold, is that this matrix also changes differentiably with respect to its position P. And so if I write it in a coordinate system, it's really the case, and sorry for the zoomers, I'm going to sit back here again one more time, that this little G matrix is a function of P. This is only defined at the point P, which again, function of P, if I'm in a coordinate chart, really means a function of these xi coordinates. So what I can say is that Gij, the ijth entry of this metric matrix, is really a function of the coordinate x, which is really n inputs. Okay, and what I need is that this Dij functions as a function of my coordinates are I need them to be at least C1 differentiable functions. Okay. And again, depending on the smoothness of your manifold, you might have a K differentiable manifold. You may want this to be CK. You want it to be the same differentiability as whatever your manifold is. Most of the time, it's easiest just to think of everything being infinitely smooth, so we don't have to worry about how differentiable everything is. It would say smooth to mean, C infinite, which is what we'll assume most of the time in this class anyway. Okay. So this you could call property, we're not one here, 1.5, 2, 3. The last thing you need for a Riemannian metric is you need it to be differentiable in coordinates. And again, this is for all coordinate systems. If I change to a different coordinate system which overlapped at P, it would just be a change of basis. The ddxi's would become ddyi's, let's say, and that change of basis, because both are smooth functions, and again, my charts are compatible, I just have a change of variables, and this G matrix would completely change. But again, if I also change the basis for U and V, I get the same answer for the dot product. And this is why we have to go through this definition of a dot product, because under change of basis, under change of coordinate systems, I want to have the same answer as for the same two vectors, they should have the same dot product. Okay. All right, any questions? As I expected, I did not get to describing how we get source paths. I thought I would probably run out of time. So on Thursday, we're going to see how this Riemannian metric, this concept of an inner product, we can talk about tangent vector norm by using the Riemannian metric. And that means we're going to be able to compute now curves on a manifold, and we're going to minimize that length to get the equations for geodesic curves, shortest path. Okay, that's the third. All right, thanks everybody.